Good afternoon or good morning, everyone. My name is Wade and I am from the University of Cape Town. I am a second year PhD student, and my supervisors are Professor Chris Reason and Dr. Ross Blamey, who also did some work on atmospheric rivers. And I will be talking about the impact of atmospheric rivers and in particularly looking at large summer rainfall events, so in the drier months, and the importance in mitigating droughts in the Western Cape of South Africa. So I'm not sure if you all are aware, but in recent years, Cape Town was experiencing a severe drought, what's more commonly known as day zero, and this refers to the dam levels reaching 0%. The dams were dangerously low at around 13.1%, and actually at 12%, the water becomes unusable because it's difficult to pump clean water out and actually provide communities with drinkable water. And as a result, severe restrictions were placed on communities. And this obviously had a strain on communities, but also, if we look at it economically, on businesses and tourism. And it was not a good year for the Western Cape, if I must say. So, a bit more on my region. The Western Cape is a winter rainfall region in that most of its rain falls in June, July, and August, which is a lot like Southern California, the Mediterranean, and Southwestern Australia. We also have similar vegetation as well. Mahlalela et al., as well as a few other papers, suggested an early winter drying, in that where, for example, where your rains would start in April, they now start a bit later in like late May, which might also have contributed to the day zero drought. Another thing, 2015 to 2017 were three of the driest years in recorded history. And this on top of this rain deficit, there was also a lack of leadership in that there was very poor governance in the region, in that it's the classical he said, she said, where scientists will give politicians advice and politicians would just turn a blind eye to actual science. And that was actually another contributing factor to day zero. However, thanks to communal efforts by around 5 million Cape Town residents, we managed to defeat day zero. And this is considerable because we did it through curbing our water use to around 50 liters per day, which, yes, it did include flushing the toilet as well as showering. Um, However, if we look at it, this was quite significant because the Western Cape has a big tourism industry. It's one of the Cape Town is one of the major cities. If it's known as the mother city in South Africa, and it's also home to a large agricultural sector in that a lot of the fruits that are cultivated in the region are exported. So if we think of our citrus fruits, stone fruits, as well as grapes and wines, the region is particularly known for that. So if we think about rainfall being more variable in recent years, and if we consider climate change, we have to realize that what happened in Cape Town and the Western Cape did not happen in a vacuum. There are multiple regions. If I can think about just a few, I know Istanbul in Turkey was running out of water, South, as well as Australia, which was also experiencing a drought right after day zero. So if we think about that and we think about populations, especially in a country like South Africa that is increasing, we have to consider that communities would have to come up with practical solutions in which they can combat climate change in their own ways that are unique to them. And I think in this way, I hope that my research may help um, poorer communities to cope with the ever going changes of the climate. So a bit more on my region. These are just lines of evapotranspiration. And as you can see, I used around 30 stations. And next to it, you can see the location of all of the six major dams, Teerwaterskloof being the highest, the largest dam, and then just going down where purple being the smallest dam. And then the star is just the city of Cape Town in relation to the location of the relevant dams. So if we look at our drier October through to March months and the rainfall patterns that we can see that the mean total rainfall and the rainy days, they mirror quite nicely in that the southern Cape, for let's call it the Southern Cape, known as the Overberg region, experiences a lot of rainfall. And this is partly because the further east you go along the coast, the more it tends from more of a um, winter rainfall region to a all year round rainfall region. And this could partially be why that region experiences more rainfall. However, on right behind it is the Cape metropolitan area here, which experiences rainfall. And then if you go further north, you see that it becomes less and less. And this is because the region starts to tend more to a semi arid to arid zone and becomes more desert like. So if you think of Namakwaland and the Karoo and the Kalahari, you're lucky if you probably get a large rainfall event in a particular season. So the major rain-bearing systems that we can, let me just move me there. The major rainfall systems that we find usually in the in the summer region, but also the winter region, is your cutoff lows, which are deep chord convective low pressure systems, which form in the Southern Ocean and make their way to South Africa and will often persist for 3 to 5 days. In contrast, there are also atmospheric rivers which contribute to rainfall, which is what we are focusing on. And these are narrow plumes of moisture which make their way from the South American coastline down towards South Africa. And this is a picture from Blamey's study, which he did in 2018 on winter atmospheric rivers. So how do we identify large rainfall events? I used the same criteria used by Ramos et al. As well as Blamey et al., which is as follows, and they calculate an R value, which is M times N, where N is your percentage of stations which cross the 90% threshold. Mind you, the papers do consider a 95% threshold, but because we are dealing with a particular time in the year where rain is far and few between, I lessened it a bit, and particularly to consider the drier regions um, of the Western Cape. And then I also looked at your mean sum rainfall anomalies, which is also another thing they did. So if we look at our top 75 events and how they are distributed over the past 40 years, we can see that the first 20 years show a large amount of large rainfall events, and then you can also see the last 20 years having a lack thereof. And this could also account for why the region was experiencing day zero. And then if we also look at the largest rainfall event per season and the percentage contribution of total rainfall, we can see that in some cases, the largest rainfall event per season can actually contribute around a third of the rainfall, which might not seem like much, but if you think about it in layman's terms, that one rainfall event over a period of 6 months can contribute a third to the rainfall, just is testimony to, yes, how dry the region may be during the summer, but also how significant these large rainfall events can be. And utilizing these large rainfall events might be the way of the future. So what I did was I looked at the top 20 events, and as you can see, it's dominated by cutoff lows and atmospheric rivers. Of the top 20 events, 9 of them were atmospheric rivers. There is no real pattern from what I can gather yet in when cutoff lows and atmospheric rivers occur. However, cutoff lows tend to occur more in the transition months, so October and March, whereas atmospheric rivers occur around October, November, particularly November. So if you look a bit more on rainfall, we look at the standardized anomalies. Again, we can see this recent drying, looking at the negative anomalies in recent years. And then if we can dissect our events, we can see that naturally most of the events that occur are cut-off lows. However, atmospheric rivers are not far behind, and it could be a case of one atmospheric river contributing per other season. So if we look at the case study, I chose the largest cutoff low and the largest atmospheric river of each of the large rainfall events. And the blue line is your dew point temperature, and your black line is your ambient temperature. And as you can see, there is a cape in A, B, and C, which is your cutoff low event. In the middle, you can see a slight cape, and this forms around from 400 hectopascals to around 500 hectopascals, which falls in line with where a cutoff low forms, because it forms in the mid atmosphere. In that is the major difference between, from what I gather, from a cutoff low and an atmospheric river. An atmospheric river also, you see the sudden increase in the dew point temperature, and it just snaking with the ambient temperature, and this means that the air then is the atmosphere is then saturated, and then it starts raining out. But you see that actually moving quite quickly away once the rainfall, which again, it just ties to the duration of an atmospheric river is much different to a cutoff low. So if we look at the moisture fluxes, A, B, and C being the cutoff low, and D, E, F being the atmospheric river, you see this beautiful cyclonic clockwise motion of a low pressure system in the southern hemisphere. And this persisted actually this particular one persisted for 5 days over the region. Whereas with an atmospheric river, you don't really see that. What you do see is this beautiful gray band, which just makes its way from South America off the Argentinian coastline down to South Africa. And you can see that this also doesn't persist for as long again. So if we consider the two different rain-bearing systems, A being the cutoff lows, B being the atmospheric rivers, this is also, A is all your cutoff lows in recorded in the top 75, and how many times it would hit the station percentage-wise. So you can see that in the southern coast, cutoff lows are very dominant. They almost certainly hit always on this area, whereas with atmospheric rivers, they start raining out once they start making landfall. So already in the Cape region, it starts raining out and around the False Bay area, whereas once it gets to further east on the south coast, it doesn't rain as much, which is another difference compared to when comparing the two rain-bearing systems. So if we look at the rain-bearing systems and how they contribute in terms of dam volumes, we can see that atmospheric rivers contribute quite a bit in terms of dam volumes. Particularly if we look at the largest dams, like Theewaterskloof being the largest, and then Voorvlei and Berg River being the second and third largest respectively. We can also see then that cutoff lows, although yes, they are important and they do contribute considerably as well, but you can see that Steenbos lower and upper, which tend more towards this region here, they cutoff lows contribute more to them. And that being said, the smaller dams do have this thing where water is moved around from time to time in order to satisfy specific needs, but these aren't that far from one another. They literally about a kilometer away from one another. So both atmospheric rivers and cutoff lows do contribute considerably to dam volumes. So if we look at the top 20 events, and compare dam percentage increases versus your R values, we see that atmospheric rivers tend to have lower R values. However, they are still on par when it comes to um, dam percentage increases. And this low R value is partly because they have a lower N value, which is the amount of stations that the particular event will hit. So, because cutoff lows persist for longer and they can actually be stationary over a region, they cover a larger area compared to atmospheric rivers, which are more short bursts of intense rainfall. So, in conclusion, summer rainfall, large rainfall events can help combat winter spring droughts and help communities recover from them. Most of our rainfall comes from cold and atmospheric rivers. Atmospheric rivers are very intense and they produce a lot of rain once they make landfall, and but they cover smaller areas, but they manage the areas that they do cover are quite effective in that it reaches where the dams are. So what might be the case is they might look into new dam prospects where um, which cover the similar areas, which are also influenced by both cutoff flows and atmospheric rivers. Cutoff flows persist for longer, and they cover relatively large area, but they don't differ that much in terms of actual rainfall volume.